So when we're looking at our exponential equation, we have y equals a times b to the power of x. And that a, remember, that's our initial amount. So when I'm looking at my first equation here, my initial amount is going to be a 2 because it's outside that parenthesis. It's listed first. It's not raised to the exponent. And then this b could be a growth or decay. And today we're going to talk about growth factors and growth rates. So that's going to be whatever's raised to the exponent. So that's my growth factor. So 1.25. My growth rate is really saying what percent is that increased by. So to go from a growth factor to a growth rate, which again is going to be a percent that it's growing by, what I'm going to do is I'm going to take my growth factor minus 1, and then I'm going to multiply it by 100%. So I'm going to do this first, and then I'm going to multiply by 100. So in this case, I'm going to take 1.25 minus 1, which would be 0.25. I'm going to multiply by 100, which would equal 25%. So that's just the formula that we're going to use. Let's look at another one here. Initial amount, that should be 3. Hopefully these first couple are pretty easy. Growth factor is 1.05. And then I'm going to take that growth factor and subtract 1. So 1.05 minus 1. And essentially what I'm doing is getting that decimal, and then I'm now going to put into a percent. And that's what I do when I multiply by 100. So it's something that's growing by 5%. Think interest. Sometimes that's how populations would grow. Let's look at number 7. That one's a little different. Initial amount is still 5,403. My growth factor is 3.1. Nothing new with that. And then my growth rate, I still use the same idea. So I'm going to subtract 1. And then I'm going to multiply by 100. So this would grow by 210%. Sometimes that can be mold that can grow pretty fast. Also things that could grow really fast would be if there's no, if you have a population of a particular animal and there's nothing that would stop it. It's like an invasive species. Those can grow pretty fast until something is done to stop them. Think zebra mussels, those grow really quickly. Then we have, so you're going to, if you want to look at the answers to the rest of them or see any more, again, that will be on Canvas. A successful small business made $10,000 in profit in the year 2000. Then the profit began to increase by a rate of 8% each year. If this trend continues, we want to write an exponential growth function. So now I'm going to go from a percent, so that growth rate, and I want to go to a growth factor. So let's put some notes on that. So if we have a growth rate, again, that's my percent, and I want to go to a growth factor, I'm going to take that 8% and I'm going to divide it by 100. I should write it out in words first. We're going to take our growth rate and I'm going to divide by 100 because I'm going to put it into a decimal. So it's in a percent, put it into a decimal, and then I'm going to add 1. And that 1 is really representing the amount of money that I already had. Like that's saying I start with 100% of my money. I'm not losing my money, but I'm getting extra. So in this case, we have 8%. So I'm going to do 8 divided by 100, which equals 0.08. And then I'm going to add 1, equals 1.08. That's not my whole equation. That is just that initial my growth factor. So my equation, I took all my room for notes. Y equals 10,000 times 1.08 to the power of x. So I'm keeping all my money and adding an 8%. To figure out in 2015, this is going to be 15 years later because I started in the year 2000. So x equals 15. So my work is going to be 10,000 times 1.08 to the power of 15. And I'm going to put that into the calculator. Hopefully I don't have to deal with adds. 1.08 And that's that XY button. I'll do 15. And then I'm going to multiply it by 10,000. So that would mean in 2015, it'd be $31,721. It's money, so I'm going to keep it 2 numbers after the decimal point. In 2025, X would equal 25 because we're just looking at how many years from 2000. So equations similar. We're still using that 1.08. And I would do 1.08 to the power of 25 and multiply by times 10,000. So this would say 68,000. Make that into a dollar sign. $484.75. So let's try one more. We have a couple different things here. So on this one, now again, I'm giving you an equation. We know that biologists could predict the rabbit population using this equation. This is where the P is the population in millions and N is the number of years. So the growth factor, that's the one that's in my equation, 1.2. The growth rate, remember, I'm going to just subtract 1. And then I'm going to multiply it by 100 to get 20%. Initial population is really 1.5 million because it's in millions. How many years would the initial population double? So what I'm going to end up doing is I'm looking for when is that, I think that was at a 1.5 or is that a 15? Let me just make that bigger. It's a 15. So that should be 15 million here. So what I'm looking for is when is it going to be 30 million. So what I can do is I can type in my equation, and I'm just going to start with 15 and then times 1.2. So I got 18. And I'm just going to kind of write like a little running total. This is 1 and 18, making my table here. 2, I'm going to do times 1.2. Just keep multiplying by the growth factor. 21.6 times 1.2, 25.92. Times 1.2, and I got 31.104. So it's going to take 4 years. You could also play around with just putting in different values for N, but usually it doesn't take too long, especially with the growth rate's a little bit bigger. And if I'm asking you one, it's not going to take forever to find. So making that table makes it easy. I'm not asking you to find the exact time that it's 30. I just want to know when it's going to be above. So 4 years is better than 3. Let's do one more of filling in a table, and then you have other pieces that you can be practicing as well. It says Sam was in 7th grade. His aunt gave him a stamp worth $2,500. Sam considered selling the stamp, but his aunt told him if he saved it, it would increase in value. So at year 0, we're not going to worry about a particular year. We're just going to say, like, when he got it, it was worth $2,500. And then we're going to look at 1 year at a time. So if we look at this again, we have a growth rate, and we're going to put it into a growth factor. So 6 is a decimal. I'm going to divide it by 100 to get 0.06. And then I add 1 to that. So my growth rate equals 1.06. So what I'm going to end up doing is taking that 2,500 times 1.06 to get 2,650. And then I multiply it again times 1.06 because that's how I get from 1 year to the next. And so is it growing exponentially? Yes, because we are multiplying. We are multiplying. To get the next number. And then our equation is going to be our initial amount times our growth factor. So we can't just put that percent in there because otherwise it would disappear, or it would it would go away. If we put in 0.06, we're not going to actually be growing. We're going to be decreasing. And then we do this again, and that we'd have a different percent, and we're just going to kind of compare the differences between those. These, we're going to put these into growth factors. And again, I'm going to take that, for example, the 150, and divide it by 100, and then I add 1. So it's just a formula again. So all these answers will be on Canvas. So if you want to check the answers and make sure that you understand what you're doing, you can look back there.